Hello, I was thinking of doing a video on bugs, and by bugs I don't mean six-legged creatures that walk across the floor. I'm talking about listening devices, miniature transmitters, whatever you call them. I've had a long fascination with bugs, right from when I was a kid in the 60s and 70s. Used to watch these spy films and TV programs where these agents would bug an apartment or an embassy, and they'd use something, well, about the size of a button, which had no visible aerial, no visible power source, and it would work for months and it would transmit for miles, which is of course a load of rubbish. Devices were just not available of that size in that era. I mean, they did have bugs, but they were fairly large back in the 60s. They'd probably have to hide them somewhere, like under a floorboard. Or the other common one was stick them inside a telephone and then use the power coming down the phone line to power them. So, you know, bugs have been around for quite a long time, and they probably have got to the point now where they're really, really tiny. But back in the early 90s, when I was working a certain government establishment, I thought I'd like to try and build a bug. Not that I had any intention of wanting to bug anybody, but I just wanted to see what I could do and how good I could make one. So I've got a couple on the bench in front of me, and I'll go through the first one I made, which is basically a replica of the one I made back in the 90s. So here's the circuit diagram of the first one I made back in the 90s, although probably before that I'd made simple ones that you could see in magazines, designs for ones that worked on FM, broadcast band. And they were fairly crude, fairly crap, you know, they drifted like hell because they were free running oscillators, and they were fairly useless, but it was something to play with, I guess. Anyway, this one is a bit more sophisticated. I had certain design parameters when I built this. It would be as small as I could make it. It turned out to be about the size of a matchbox in the end, because I didn't have surface mount components in those days. But it would have to work on a roughly 3 volt supply, a couple of AA batteries or a couple of rechargeable batteries, and current consumption is absolute minimum. I think I got it down to about 3 milliamps, and the output power would have to be about 1 milliwatt, which would give it a range, as I found out, of about 100 yards, which is not too bad. And it's the basic circuit of it. It's got a little microphone at the beginning, which is a condenser microphone. They're fairly small and fairly good audio quality. Then a 2-stage microphone amplifier, and I've deliberately selected components that give it absolute minimum of current draw. So the whole microphone amplifier, I think, was drawing about 0.3 milliamps, and it doesn't need to have any particular drive capability, because it's just producing a voltage swing to drive a varicap diode, which is connected to the crystal oscillator. I used the crystal oscillator to give it nice stability, and it's a FET oscillator, which again uses virtually hardly any current, about a milliamp maybe, and I used a 12 megahertz crystal, and that's basically having its frequency varied by the varicap diode, so you get a few hundred hertz of frequency shift at 12 megahertz. And then what I'm doing here is I've got in the source connection, I've got a small coil which is tuned with a variable capacitor, and I'm selecting the 12th harmonic of 12 megahertz, which is 144, 145 roughly. It actually comes out to about 145, 150 on the one I built a few years ago. And that 12th harmonic is coupled into an RF amplifier with about 20 dBs of gain. I'm using a high gain RF transistor, and then I'm tuning that in the collector and with a coil capacitor to peak the output, and tapping it off at a low impedance point, roughly 50 ohms, and that's coupled to a bit of wire for the aerial. As I said, it's 20 dB gain, 1 milliwatt output roughly, and the whole thing draws about 3 or 4 milliamps, which is not bad. And if I bring it into view, you can see it's not especially small. It's a bit smaller than the one I built back in the 90s. It's about 1.5 inches by 1 inch, and let's see if I can zoom in a bit. And that's the microphone there, condenser, and that's a little microphone board which I built using surface mount components. That's the crystal, which is 12 megahertz, and there's the FET, and that's the output from the FET, which is tuned to the 12th harmonic of 12 megahertz, coupled into this RF transistor, and then that's tuned on there, which goes to the output, which I did have connected to a piece of coax, but that's fallen off. But anyway, I'll connected the aerial back up, and you can hear what it sounds like. Okay, I've got it wired up now to power supply, and it's drawing about 5 milliamps, which is a bit more than I'd hoped, but never mind. And the aerial is roughly 19 inches, quarter wave on that frequency, and also it's got like a, well, it's basically a dipole because it's got an earth wire which is another 19 inches, and I'm guessing it's this crystal I'm using came out of an old 2-meter radio, because it's on 145 150, and that's the input in the UK for repeaters. And well, there are no repeaters in this area on that channel. The nearest one's about 50 miles away, so I'm not going to be causing any problems. But got it connected up, and that's listening on this radio. As you can hear, it's feeding back. And if I 1 2, it's a bit difficult to demonstrate when you're so close to it, but you know, it works fairly well for what it is. And it's narrowband FM. As I said, you get a few hundred hertz of deviation on the crystal, which is multiplied by 12, so you get a few, well, 3 kilohertz maybe of deviation when it gets to 145 megahertz. I just stick it on the spectrum analyzer. You can see what it looks like. So here it is on the spectrum analyzer, and as you can see when I talk, it's FMing the signal, and peak search is so it's on exactly 145 150 as I expected, and it's not quite producing a milliwatt, but I stopped talking. It's minus 1.5 dBm, so about 0.8 milliwatts, something like that. But you know, it works fairly well for what it is. Now I'll go on to a more sophisticated one I built after this, which is a lot smaller and uses a chip. So this is the next one I made, and I got this design off the internet. It's some Russian guy, and it really is minute. It's, where's my inches, 3/4 of an inch roughly, 3/4 of an inch by about half an inch, and it really pushed me to my limits of how I could solder something with such small components. And it took me bloody ages to get all the wires in the right place and whatever. But anyway, I'll go through the circuit design. So this is the circuit diagram. It uses this little chip. Now it's a Max 1472, and as I said, I found this design on the internet by some Russian guy, and he actually had built one which was the size of a 1-cent coin, I believe. So yeah, this chip, I think, is generally intended for use on RF remote key fobs for cars and stuff like that. So it would normally have digital data modulated onto it, but it's ideal for this application. And how it works is it's got a phase lock loop in it, and it produces an RF output between 380 and about 450 megahertz, which is in the RF key fob sort of band. They're normally on about 433.9 in this country, and it uses a crystal, and it multiplies the crystal frequency by 32 in the phase lock loop. So in this application I've managed to find a fairly commonly available 13.56 crystal, 30.56 megahertz crystal, which is multiplied by 32, which comes out at 433.920, which is ideal really, because that's in the amateur radio band, 70 centimeter amateur radio band. So as I've got a license, I'm not really committing any offences particularly, unless I really did bug somebody, but I'm not going to bug anybody. But anyway, the basic design is you've got your microphone amplifier with a little condenser microphone, and I discovered that cell phone hands-free kits have often got tiny little condenser microphones in them. They're incredibly small, and yet they work quite well. But it's basically the same microphone amplifier design as I used in the last one, except I probably used higher value components that he's got on this diagram, because it's just modulating a varicap. Where's the varicap? Yeah, there's the varicap. So yeah, the output from the mic amp is going into the varicap and modulating the crystal by a few hundred hertz, which is, or even less than that, because it's been multiplied by 32 in the phase lock loop. So any deviation on here is going to be multiplied by 32. So you don't really need much of a frequency deviation at this point. And this chip can be configured to produce any output up to 10 milliwatts. And you can change a resistor to lower the output. I think the resistor goes in line with this choke. I've left it at its maximum, which is roughly 10 milliwatts. And you've got to make tiny little coils, which are minute, and that just goes to an antenna. And the advantage of this frequency, 433 megahertz, is that the aerial is a lot smaller, only a few inches, about 6 or 7 inches. So I'll just show you as best I can what the thing looks like inside. So here it is, the insides of it. I've got it on, trying to zoom in as much as possible, and you've got a tiny little microphone. I think I need a smaller pointer. Okay, I'll try this screwdriver. That's the condenser microphone, which came out of a telephone hands-free kit. And down here you've got the microphone amplifier, which is just a couple of tiny little surface mount transistors and some resistors, sort of mounted dead bug style, which is appropriate. And I think that's the output from the amplifier, which goes to the varicap, which is down in the tiny little black varicap diode. And that's coupled into the crystal, and that's a surface mount crystal, 13.56 megahertz crystal, tiny little crystal. It's about 3 or 4 millimeters by 2 millimeters roughly, that crystal. And up here we've got a tiny little chip which is unbelievably hard to solder. It's got 8 legs on it, and I'm not using all the legs. Some of them are, 3 of them connected to positive, one's earth and whatever. So and then it's got a couple of tiny little coils to resonate the maximum output on the 433.920, and that's coupled through this another tiny little coil there. Goes through the side of the case, which is made out of sheet copper, very thin copper, and that's connected to the aerial, which is a little bit of thin wire, and the green thing is the rechargeable battery, which rather lets it down because the battery is bigger than the actual bug. I suppose you could use one of those lithium coin cells, but that wouldn't last long because this draws about 10 milliamps, so it's fairly heavy current consumption. But it really is tiny if you compare it to the size of my thumb, and it's about the limit of what I could produce. I guess if you had a PCB made in China, you could make it even smaller. But let's just connect it up and hear what it sounds like. Oh, by the way, when I was testing this, I had it hanging up in my lounge window, and I thought I'd drive over to the hill about a mile away and see if I could hear it. Well, the first problem was I couldn't unlock my car with the key fob. I sort of panicked a bit. I thought, what's going on here? The light was lighting up on the key fob, but it just wasn't unlocking the car. So I got the other key fob, spare key fob. That was exactly the same. Still couldn't unlock it. So I had to use the key to unlock the car, but that set the bloody alarm off then when I opened the door. So I thought, well, I was starting to panic a bit then. What am I going to do, I thought. So I shut the door of the car and it stopped the alarm, but went back in the house and I thought about it. It's the bug hanging up in the window. It's producing enough output to block the receiver in the car remote control receiver, because it's on roughly the same frequency. So when I worked that one out, I knew what was going on. But anyway, as I said, I drove up onto the hill about a mile away where I can see my house. It's like line of sight, and it was quite a strong signal up there about a mile away. But if you walk down the road, you'd soon lose it, because UHF's very much affected by buildings and obstacles and stuff like that. But 10 milliwatts will go quite a long way, and it would probably be receivable more than a mile away if it was line of sight, maybe 5 miles away easily. So so I'll just turn on the receiver. So here it is on my little Bofang radio, and I can talk into it, and I'm about 5 foot away now, and now I'm out in the garage, and I could walk up the garden, but I'm not going to because it's too wet and nasty today. But I think it works fairly well for what it is, and now I'm going to walk back in the shed and I'm going to turn it off. And that horrible noise was an RF thermometer, I believe. So next thing, I'll just show you what it looks like on the spectrum analyzer, and that'll be the end of the video then. So here it is on the spectrum analyzer. As you can see, there's some modulation on it when I talk into it, and I'm actually only getting about 8.6 dBm, but that's probably down to the battery voltage. If I shove more voltage up it, I'd probably get more output. I think you can put in about up to 3 volts, which would probably give you 10 dBm then, 10 milliwatts. if I change my span and increase it, you can see that it's not particularly clean. It's got quite poor phase noise, but you know, it's just a simple little PLL chip. It's not designed to be ultra pure output signal. I'm on a 10 megahertz span now, so it's got quite a lot of noise. I go just about a megahertz away. It's only about 25 dBs down the noise of the phase noise. So that's about it really. That's the end of the video. Thanks for watching. Bye for now.